Hello friends, today I will discuss about what is percentage impedance of the transformer and its importance in substations. So percentage impedance of the transformer, which is nothing but the per unit value of the impedance of its own base MVA. For example, if a transformer capacity is 10 MVA and it is a 33 by 11 kV transformer and its percentage impedance is 8%, then per unit value of the transformer impedance is 0.08 per unit to the base MVA is 10 MVA. Again, when the transformer is fully loaded condition, that is due to flow of the rated secondary current, a voltage drop take place due to the transformer winding resistance and reactance. And this voltage drop is expressed in terms of rated voltage, which is called as the percentage impedance. So percentage impedance is the ratio of the voltage drop to the rated voltage is the percentage impedance. Now let us take a simple example. Now if the primary winding rated voltage is 33 kV, that is 33,000 volt, and is fully loaded, and the measured voltage drop is 330 volt, then the percentage of the voltage drop which is expressed as the rated voltage, that is percentage of voltage drop is 330 divided by 33 kV or 33,000, which is nothing but as the 10%. That is 10% voltage drop will occur if the transformer is running under in full load conditions. So the percentage impedance of the transformer is 10%. Now again, the percentage impedance of the transformer can be defined as the percentage of the rated voltage required to circulate rated current in either side by keeping other side shorted. That is, if percentage impedance of the transformer is Z, and then if you supplying rated Z% of the rated voltage to the HV side by keeping LV side shorted, then rated current will flow in the LV side. So Z is the percentage impedance of the transformer. Now, how to determine the percentage impedance of the transformer? In order to determine the percentage impedance of the transformer, short circuit test is done. In order to carry out the short circuit test of the transformer, normally a variable voltage supply is given in the LV side by keeping HV side as shorted. So in this case, a voltage supply is given from the auto transformer and voltage is gradually increased until and unless the full load current flow in either side of the transformer by keeping HV as shorted. So at that voltage, at the voltage at which the full load current flows, this voltage is recorded by means of voltmeter. So we can get this value of the voltage, and also we know the rated voltage. So the percentage impedance of the transformer is this voltage divided by the rated voltage. Now let us take a simple example of the HV side voltage of the transformer is 11 kV and LV side voltage of the transformer is 415 volt. And transformer percentage impedance is 4% and kVA rating of the transformer is 100 kVA. So the full load current in the HV side, that is IFL in the HV, is equal to the kVA capacity, that is 100 divided by root 3 into 11 kV, which comes as 5.25 ampere. Again, full load current in the LV side is equal to 100 into 1000 divided by root 3 into 415, which comes as 139.12 ampere. Now a short circuit test is carried out by keeping LV side shorted and a variable voltage supply is given in the HV side by means of auto transformer, and voltmeter, ammeter and wattmeter arrangement is done in the HV side. So the voltage is gradually in the HV side until and unless the rated current flow in both the side of the transformer. So at the voltage at which the rated current flows, this reading is recorded by means of voltmeter. So percentage impedance is equal to voltmeter reading divided by V rated. Now, if the since the percentage impedance is 4%, so 4% of the rated voltage is sufficient to cater the full load current in the either side by keeping other side as shorted. So here the V reading would be 0.44 kV and V rated is 11 kV. So percentage impedance is equal to 0.44 divided by 11 comes as 0.04 or 4%. Now, why transformer impedance is given as a percentage? The percentage impedance is also called the per unit impedance of the transformer for its own base MVA or kVA rating. For example, if a 33 by 11 kV 10 MVA transformer has percentage impedance of 8%, then per unit value of the impedance of the transformer to its own base MVA, that is 10 MVA, is 0.08 per unit. Now the base MVA is 10 MVA and base kV in the HV side is 33 kV and base kV in the 11 kV LV side is 11 kV. Now with respect to HV side, now we can calculate the base current is equal to the MVA base into 10 to the power 3 divided by root 3 into kV base. So ZB, that is base value of the impedance in the HV with respect to HV side comes as kV base divided by root 3 into base current into 10 to the power 3, that is equal to kV base into 10 to the power 3 divided by root 3. Now base current, which is equal to MVA base into 10 to the power 3 divided by root 3 into kV base. So by putting this value, we can get the root 3 as a cancel out, and we get the ZB value, that is base value of the Z is equal to kV base that is whole square divided by MVA base. So Z is equal to kV square divided by MVA. Now the Z base, that is the base value of the impedance, is nothing but equal to kV base square divided by MVA base. Now with respect to HV side, that is 11 kV side, the base value of the impedance is equal to 11 into 11 divided by 10, which comes as 12.1 ohm. That is the base value of the impedance with respect to HV side. So actual impedance with respect to HV side or 11 kV side comes as Z per unit value into Z base, which is equal to 0.08 into 12.1 comes as 0.968 ohm. So this is the impedance of the transformer with respect to HV side. Now again, with respect to 33 kV side, the value of the base impedance is equal to 33 square divided by 10, which is comes as 108.9 ohm. Now actual impedance, that is ZA equal to Z per unit into Z base. So actual impedance in the with respect to HV side, that is 33 kV side, comes as 0.08 into 108.9, which is equal to 8.712 ohm. So you can see the difference of the actual impedance with respect to HV side and LV side of the transformer. So we can see that the actual impedance which is referred to 33 kV side is equal to 8.712 ohm, but in case of 11 kV side, the actual impedance comes as 0.968 ohm. So actual impedance with respect to 33 kV side is 9 times that of the actual impedance with respect to 11 kV side, since the turn ratio is 3:1. So separate if the impedance is expressed as a percentage, then separately it is not necessary to mention the value of the actual impedance with respect to HV side and LV side. So if we express the impedance of the transformer as a percentage, then it will be sufficient. The role of percentage impedance in case of parallel operation of the transformer. So if the two transformers are running in the parallel condition, then how the load is shared? that will be depend on the percentage impedance of the transformer. The load sharing of the transformer is directly proportional to the MV or kVA capacity of the transformer and inversely proportional to the percentage impedance of the transformer. That is, if the two transformers under running in parallel condition, then the transformer which has the less percentage impedance will cater more load compared to the other transformer. Now consider the two transformer, that is transformer 1 and 2 are running a parallel condition with having percentage impedance of Z1 and Z2 respectively, and total load is IL, and therefore the I1, that is the load shared by the transformer 1, will be equal to Z2 divided by Z1 plus Z2 into IL, and load shared by the transformer 2, that is I2, is equal to Z1 by Z1 plus Z2 into IL. Now let us an example. The total load is 100 MVA and the transformer capacity of the two transformer is equal, that is 50 MVA, and percentage impedance also equal, that is 12%. So load shared by transformer 1 is equal to 50 divided by 12 divided by 50 by 12 plus 50 by 12 into 100. Since load shared by the transformer 1 is proportional to the MVA capacity and inversely proportional to the percentage impedance. So here the load share will be equal to 50 MVA. Again, load shared by the transformer 2 is also 50 MVA, since both the capacity of the transformer is same and percentage impedance is same. Now let us take another example. In this case, total load is also 100 MVA and the MVA capacity is same for both the transformer, but percentage impedance of tier 1 is equal to 11% and tier 2 is 13%. So load share by the transformer 1 is equal to 50 divided by 11 divided by 50 by 11 plus 50 by 30 into 100. Or we can say, since the MVA capacity of the both the transformer is same, so in this case the load share will be only dependent on the percentage impedance of the transformer. So load share by the T1 is equal to percentage impedance of the transformer 2, that is Z2 divided by Z1 plus Z2. Now here Z2 is equal to 13%. So 13 divided by 24 into 100, which comes as 54.17 MVA. Again, load share by the transformer 2 is equal to 11 divided by 13 plus 11, which is 24. So 11 divided by 24 into 100, which comes as 45.83 MVA. So we can see that since the transformer impedance of the transformer 1 is 11%, so more load is shared by the transformer 1, and since the percentage impedance of the transformer 2 is 13%, less load is shared by the transformer 2. Now, percentage impedance is an important parameter in order to determine the three-phase short circuit level of the low voltage side. So three-phase short circuit current can be calculated as the full load current of the LV side divided by percentage impedance. Now consider two number of 132 by 33 kV 50 MVA transformer are running in parallel condition and percentage impedance of the transformer are equal and is equal to 12%. Therefore, three-phase short circuit current will be equal to the LV side full load current divided by 0.5 into 0.12. Since the LV side full load current as 874.80 ampere, therefore the three-phase short circuit current comes as 14.58 kiloampere for 33 kV bus fault. Now consider four number of transformers running a parallel condition with same capacity and voltage rating is same, and the percentage impedance of the transformer are equal and is equal to 12%. In this case, three-phase short circuit current will be equal to LV side rated current divided by 0.12 divided by 4, which comes as 29.16 kiloampere for 33 kV bus fault. So if the phone number of 132 by 33 kV transformer with MVA capacity 50 MVA running in parallel condition, then in this case the short circuit three-phase short circuit current will be equal to 29.16 kiloampere for 33 kV bus fault, or if the three-phase fault occur very close to 33 kV bus. Now the 33 kV CV, that is which is designed only for 25 kiloampere for 3 seconds, the short circuit capacity of the 33 kV CV. Since the fault current is much greater than the CV short circuit capacity, which is 25 kiloampere for 3 seconds, this CV cannot withstand this type of fault current. So in this case, phone number of transformer cannot be parallel. So percentage impedance is an important parameter in order to determine how much number of transformer can be running under parallel condition. So friends, if you like my video, then do subscribe my channel and also press bell button for notification of videos to be uploaded in future. Thank you for watching my video.